Hello friends, welcome to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are starting this course today with module 1. We are in lecture 1 and this is entitled Introduction. Now, before going into the actual lecture, I would like to give you an idea about the concepts that we are going to cover during this course. This course we have divided into 12 modules. Module 1 will deal with watershed hydrology, and we will talk about introduction, then we will go to precipitation and its forms. We will also talk about rainfall measurement, presentation of rainfall data, then we will talk about consistency check of rainfall data and estimation of mean aerial rainfall and missing rainfall data. Then module 2 will primarily deal with hydrological processes, that is, we will talk about interception, infiltration, factor influencing infiltration, measurement and indices, evaporation, its measurement and estimation of evapotranspiration. We will also carry out exercises on the computation of evaporation, evapotranspiration and infiltration indices. Module 3 will discuss about stream flow processes, that is overland flow and subsurface flow. We will talk about the stream flow measurement, basically measurement of stage, velocity and stream flow itself. Then we will talk about stage discharge rating curve. We will discuss flow duration curve and flow mass curve. Coming to module 4, it will deal with runoff, that is the factors affecting runoff, estimation of peak runoff rate and volume, Cook's method, rational method and SES curve number methods of estimating peak runoff rate and volume. And we will also include several computational problems of estimating peak runoff rate using Cook's method and rational method, and computing runoff volume by SES curve number method. In modules 5 and 6, actually these are two combined modules where we will talk about hydrograph, that is the components of hydrograph, base flow separation, unit hydrograph theory, S curve, that is summation curve, synthetic hydrograph and applications of hydrograph theory as well as the limitations of the hydrograph theory, and we will carry out exercises on runoff hydrograph, unit hydrograph and synthetic unit hydrograph. Module 7 will talk about drainage basin characteristics, that is geomorphology of watersheds, linear, aerial and relief aspects of watersheds, stream order, drainage density, stream frequency, and then we will carry out exercises on geomorphological parameters of watersheds. During module 8, we will talk about hydrological modeling, that is the concept, protocol and classification of hydrological models. We will discuss the basic steps of model calibration, model validation and carrying out the sensitivity analysis of model parameters. In module 9, we will focus on floods, that is we will discuss the terms and definitions. We will talk about headwater flood control methods, determination of flood peak, design flood and computation of probable flood. Module 10 will deal with flood routing, that is channel edge reservoir routing, where we will discuss hydraulic and hydrologic routing methods and will carry out exercises on flood routing. Module 11 will talk about drought, its classification, causes and impacts. We will talk about various drought indices which are used, and then we will talk about the strategies for drought management. Module 12 we have kept for recap of concepts that we will be covering in first 11 modules, and also will include doubt clearing, that is answers to questions raised by students during entire session, and I will encourage students to ask questions so that we can clarify those doubts in those lectures. Now, coming to content of this particular lecture introduction, here we will talk about learning outcomes, we will talk about global and India's water resources, we will define hydrology, we will discuss about hydrological cycle and we will see hydrology applications. Now, before going into the course content, I would like to talk about learning outcomes. And in technical education, basically for analyzing the learning outcomes, we adopt Bloom's taxonomy of educational objective, which was developed by a group of educational experts led by Benjamin Bloom, who was an American educational psychologist. And this taxonomy was developed first in 1956 and then it was revised in 2001. Now, as per Bloom's taxonomy, there are 6 levels of cognitive skills starting from low to high. And before going into these skills, I would like to define cognition. So, cognition is the mental action or process of acquiring knowledge and understanding through thought, experience and senses. That means anything we do in order to learn a thing, that is cognition, and typically human beings have 6 levels of cognitive skills starting from low to high. And these 6 levels are starting with knowledge and remembering. If you look, there are 2 terms at each stage, and the first term at each level was given in 1956 when it was first Bloom's taxonomy first came into existence, and later on these terms were modified in 2001. So, it started with knowledge, but now it is called remembering. This is the lowest level, and I think we all recall that when we were toddlers, our parents, especially our mothers, while working even in kitchen, they were asking us to repeat A, B, C, D, 1, 2, 3, and that is how we remembered all those letters and numerals. That is the first or lowest level of. So, once we remember those letters, then we start understanding, and that is how it comes that A for apple, B for boat, C for cat and so on and so forth. So, we start linking those what we have remembered, we try to understand with other objects. And then once we understand and remember, then we start applying our knowledge. And once you apply, you have to analyze and evaluate. And once you have applied, analyzed and evaluated, then of course, you reach the highest level, which is creation or creating. Now, as far as this course is concerned, that is how we are going to link is that after successful completion of the course, students shall be able to fulfill these objectives. If you see here, I have used a color code. Black is at lowest level. I am not using that in our subject because it goes without saying that you need to definitely remember certain things in order to do whatever. So, that is what, but red color is understanding. So, that starts with the student shall be able to understand and explain the fundamentals of various hydrological processes. They should be able to apply and analyze, that is level 3 and level 4, the hydrological data for hydrological modeling. They should be able to demonstrate and evaluate hydrological models dealing with various hydrological processes, and once they are able to understand, explain, apply, analyze, demonstrate and evaluate, then they will be capable of developing solutions to real life hydrological problems. So, these are the learning outcomes, and I expect that after successful completion of course, the students shall be able to perform all these basically. Now, coming to global water resources, as we all know that we basically live in a world of salt. That is simply because around 97.5% of water which we have on the earth, that is in the form of salt water, and only 2.5% of water is in fresh water. And out of this 2.5% fresh water, around 69% lies in glaciers and permanent snow cover, 38.8% is groundwater including soil moisture, swamp and permafrost, and only 0.3% of water, only 0.3% of water lives in, or it is which we can really see with our naked eyes, that is in lakes and reservoirs or river storages. And if you just count it, then this 0.3% actually amounts for 1,05,000 cubic kilometer of water, total water, or just a minuscule 0.0076% of the total water resources. So, that is what we really use and we need to bother about. Now, coming to India's water resources, we have 2% of global landmass. India has 2% of global landmass and 4% of world's renewable water resources, and we support around 17% of global population. So, that itself is a big challenge, that with 2% of global landmass, 4% of world's renewable water resources, we need to support 17% of global population, and that is why it is no surprise that when it comes to per capita water availability, we rank 50th in the world. So, we are 50th in the world when it comes to per capita water availability. So, that's so water is very precious for us from that perspective. Now, 80% of our precipitation occurs during monsoon season, that is during June to September. So, that is also is a challenge for us, and influence of Himalayas on the monsoon, that creates further challenges for as far as India's water resources are concerned. Now, coming to India's water resources or India's water mass, we have a total of 4,000 billion cubic meters of water, and out of which available water is 1,869 billion cubic meter, and out of which this is available because 1,047 billion cubic meter is lost in evaporation and 1,084 billion cubic meter is non-available. As far as available water 1,869 billion cubic meter concerned, only 1,123 billion cubic meter is usable water, and if we still break these usable water, around 728 billion cubic meters of this water comes from surface water sources and 395 billion cubic meters comes from the groundwater sources. Looking at India's water demand, which was around 829 billion cubic meters in 2006, that is projected to go up to 1,093 billion cubic meter in 2025, and it is projected to be 1,047 by 2050. So, as you see that between 2025 and 2050, there is a projection of decline in water demand, and that decline basically is because it is expected that our population will decline and get stable, and also water use will become more efficient, because every day we are getting very efficient water efficient gadgets. For example, in our household kitchens now we have dishwater, which uses only about 1/20th of water which was being wasted earlier when these dishwashers were not being used. So, that is why the water use efficiency will go up because of the modern gadgets. As far as per capita water use is concerned, in 2000 our per capita water use was 88.9 liters per day, which is likely to go up, projected to go up to 167 liters per day, and that is because of the changes or improvements in our lifestyle. If you look at China, the numbers are more or less similar. In 2000 it was 82.7 liters per day, and 2050 it is projected to be 155.4 liters per day. But if you look at the US, the numbers, staggering numbers, because they are probably one of the largest users of per capita per day water, and in 2000 the values were 582.7 liters per day, but they are projected to go down to 484.6 liters per day in 2050. So, we are pretty stable in the sense, but not in comparison to the advanced countries like US. Now, coming to water use share percent in various sectors, especially we will talk about agriculture, industry and domestic. If you look at India, most of our water use in agriculture sector, that we use around 83% of our water resources in agriculture sector, 12% in industry and only 5% towards domestic uses. If you look at Europe, corresponding numbers 33% only in agriculture, staggering 54% compared to 12% in India goes to industry and 13% in household. So, as you can see that the industrial water use shows that they are more industrialized countries and they are more advanced countries. And if you look at the world numbers, the world average in agriculture is around 69, industry is 23 and household is 8. So, probably it is a water challenge that we need to reduce the water consumption in the agriculture sector and increase in industry and domestic sector. Now, coming to major river basins in India, we have around 12 major river basins which have catchment greater than 20,000 square kilometers, and we have 48 medium river basins. And if you look at the map, then you can see that these major basins are Ganga, Brahmaputra, Meghna, Subarnarekha, Brahmani, Baitarani, Mahanadi, Narmada, Tapi, Sabarmati, Mahi, Krishna, Godavari, Pennar, Kaveri here, and there are some east flowing and west flowing rivers other than these major rivers. But if you look in a nutshell, the Ganga, Brahmaputra, Meghna, which accounts for 8,61,452 square kilometers of catchment area, that accounts for around 62% of the total water resources of the country, or out of 1,869 cubic kilometers of water, it accounts for 1,160 cubic kilometers of water. So, that is very significant from India's water resources point of view. Now, coming to this course watershed hydrology, we will begin with defining watershed, and watershed could be defined as any portion of the earth's surface within a physical boundary defined by topographic slopes that divert or run off to same drainage outlet. So, if you have any drainage area and if it drains water to a single outlet, then we can call that as a watershed, and this is also shown in this picture here. Now, the advantage of this definition is that it permits the selection of any watershed outlet desired, or it facilitates sub watershed study. As you can see here that this one large one is there, this one, if you talk about this one, this is a watershed as per our definition, because the topography is such that the entire water will be draining to this outlet number 4 here. Now, the advantage is, I said that this definition allows us to select watershed anywhere. Now, suppose I want to select watershed here, I want, this is the point of my interest, then knowing the topography, I would require to delineate this area. Say I can delineate this area, so that becomes the catchment, and entire water from this area, if topography is okay, then that will be draining to. So, we basically we require a topographical map for deciding the drainage divide. So, a watershed is defined with respect to outlet, and any point on the main drainage system can be selected as the watershed outlet. So, that is why if I have a water project here at this point in this river, then this point, this becomes my watershed and this becomes my portion of interest rather than this. So, depending upon which outlet is of concern, I can delineate the watershed or the larger watershed, and then I can work on that. At this point, I would just like to mention that watershed, basin and catchment, these 3 terms are synonymous and they are used interchangeably by hydrologists. So, many time in our discussion, I will also use basin or catchment, but they all mean the same. So, watershed, basin and catchment will be interchangeably used in our discussion also. Coming to defining hydrology, the term hydrology is from Greek hydor, which means water, and logos, that means study. So, basically hydrology is study of water. As a noun, it is defined as the science dealing with the occurrence, circulation, distribution and properties of the waters of the earth and its atmosphere. But over the time, this definition has has evolved. A lot of changes have been incorporated, new issues have been incorporated in the definition, and the latest definition or the most comprehensive definition is given in the Blue Book, which is Opportunities in Hydrological Science, published by National Academic Press in 1992. And as per the definition of hydrology is that hydrology is the science that treats the waters of the earth, occurrence, circulation and distribution, their chemical and physical properties, and their reaction to their environment, including their relation to living things. The domain of hydrology embraces the full life history of water on the earth. So, as you can see that when we were defining hydrology earlier, we were only talking about occurrence, circulation, distribution and maybe properties, but not defining what properties. But in this definition, clearly there are three distinct inclusions. One is the environmental hydrology, that is because this definition includes the reaction of water with the environment. Then eco-hydrology, because it includes relation of water to living things, and water quality, because it talks about the chemical properties of water also. So, water quality. So, these three are new inclusions, and these are the new three areas which have become a part of hydrological study over the period of time. But one of the simplest definition of hydrology was given by Penman in 1961, and Penman defined hydrology as the science that attempts to answer the question, what happens to the rain. Now, we all know what happens to rain because we have observed rainfall occurs, it is intercepted by plants and buildings, it reaches this ground surface, flow starts taking place and several other processes occur. So, basically we all know what happens to rain, and that is why it sounds like very simple question that what happens to rain, I know. But the challenge is in quantitative description of various processes that are involved in this process, in this entire phenomena, and these are very complicated basically. Hydrology could also be defined or in a more strict sense, it could be also treated as study of hydrological cycle, which of course is endless circulation of water between the earth and its atmosphere. So, hydrological cycle is endless circulation of water between earth and atmosphere, and if we study hydrological cycle, then it amounts to studying hydrological hydrology. Now, this is a picture of the hydrological cycle. This is important, and I am sure that you have also seen in your junior classes science textbooks. And so, this is typically we have an environment where clouds are there, water is there, land surface there, plants are there, sun is there. So, it all starts with sun providing the energy, and because of the heat and the water from open water surfaces or large water bodies, sea, oceans, rivers, etc., it starts evaporating. So, that process is evaporation. Similarly, plants, we all know that they transpire water from their surfaces in order to meet their water requirement. So, combined together this evaporation and transpiration, they carry water from land surface or plant surface to atmosphere, where cloud formation takes place. Then obviously, when situation arises, condensation occurs, and once condensation occurs, then precipitation takes place. When precipitation occurs, water reaches the earth's surface, a part of it gets infiltrated, and then remainder start flowing on the surface. And also, when the water infiltrates, it goes further down, it percolates, and surface flow starts taking place. So, this is what hydrological cycle is. These are various processes involved, and we will be talking about all these processes. They are already given you the concept that will be covered. As you see, if you recall, almost all these terms we have discussed, and we will be discussing about all these in our discussion. Now, from a global perspective, hydrological cycle may be considered to be comprised of three major systems: the oceans, the atmosphere and the land. The oceans is the major source of water, atmosphere is the deliverer of water, and land is the user of water. So, we have already seen that the entire hydrological cycle starts with evaporation from water bodies, that is from oceans. So, that acts as the source of water, and once water gets into atmosphere, cloud formation occurs, condensation occurs, precipitation takes place. So, water is delivered back to land, and so the atmosphere is the deliverer of water, and of course, the land when it reaches, it gets utilized for various purposes. So, land is the user of water, and the three principal processes that transmit water from one system to other are precipitation, runoff, and evaporation. And we have also again seen in our hydrological cycle discussion that it all starts with evaporation. So, evaporation is a process through which water goes from oceans to atmosphere. Then precipitation which delivers water, and runoff which flows through which the water flows on the surface and gets used for different purposes. Now, hydrological cycle can be studied at different scales. So, this we can talk about the global schematic of hydrological cycle, which has three different systems: atmospheric system, earth system, and ocean system. And of course, we know that when evaporation occurs, water from ocean system reaches to atmosphere, where precipitation takes place, and water reaches the ocean system. A part of that reaches the earth system, and from earth system evaporation or evapotranspiration takes place, and water reaches back or from earth system to atmospheric system. Earth system stream flow occurs and water reaches the ocean system, and ocean system to earth system, it might go through tidal flow or sea water rise or groundwater intrusion. So, that is why all these three systems are interlinked. Now, if we zoom into this earth system, we can also talk about schematic of hydrological cycle in the earth system, and then we will have three new systems: land system, subsurface system, and aquifer system. So, obviously, precipitation takes place on the land system, and from where surface runoff is generated and reaches the form of stream flow reaches the oceans. Then water gets infiltrated, reaches the subsurface system, from where again surface flow takes place and water reaches the stream flow. Then water gets percolated here, reaches the aquifer system, from water groundwater flow or groundwater runoff take place, and that contributes to surface flow. On the other side, if you talk about evaporation or evapotranspiration, that keeps on occurring from all these land system, subsurface system as well as aquifer system. Then from some other processes are like there is a upward movement of moisture from aquifer system to subsurface. Similarly, exfiltration, which is just a reverse of infiltration from subsurface system to land system. Now, further we can further zoom down into land system and can get three different systems, that is vegetation system, structural system, and soil system. So, here again precipitation occurs and falls on all three systems: vegetation, structure, and soil system. And then from vegetation evapotranspiration takes place, some interception occurs. Structural system also intercepts water. From here vegetation system evaporation takes place, and through fall from vegetation system goes to soil system, and from soil system moisture supply is available to vegetation system, and evaporation occurs from structural system as well as the soil system. And also the vegetation system through fall supplies water to the soil system. So, this is how we can look at hydrology from different angles at different scales. And looking at the application of hydrology, there are innumerous, if you look at the watershed or an area, there are plenty of applications of hydrology, like for determining the water balance for a region. Say watershed, we want to find out what happens, what are the quantities of different processes that can be studied. We can predict floods by studying hydrology. We can determine agricultural water balance, that means we talk about agricultural land, agricultural area, then we can talk about what happens, how much water is being used by plants or crops or and so forth. Then we can design drainage system, we can design irrigation systems, we can also assess export of sediment and nutrients from field to water system, we can design urban drinking water and sewer system, and we can assess the impact of natural and human induced environmental changes in water resources. We can also design buffers, that is the plantation that is required to check the pollution which is coming from agricultural land to the water. So, there are several applications, some of them we will see through our discussion. With this, I close this lecture. Thank you very much, and I encourage you to give feedback so that we can improve in further lectures. Also, please raise your doubts or questions through various forums which can be answered. Thank you very much.